Okay, here's the first part of our video notes on what we call additional aspects of equilibrium. So we'll talk about a lot of different things in this chapter. It's sort of a catch-all chapter. This first one will mostly be about a little bit about common ion effect and mostly be about titrations and a little bit more stuff with acid and base equilibrium. So to start off with the common ion effect, up until now we've just looked at a weak acid or base, and you can also look at these things when you have that same weak acid and base with a solution that already contains some other soluble salt. So it affects the equilibrium a little bit. If you think of this example here with acetic acid, where you have acetic acid and water creating H plus and the acetate ion, if we were to add more acetate ion, add more of this ion to the solution, Le Chatelier's principle says that the equilibrium would then shift back to the left, right, to try to consume some of this and restore equilibrium. So that's going to affect the amounts that dissolve. So if a weak acid or base is combined in a solution with its conjugate acid or conjugate base, it will dissociate less because the shift in the equilibrium is shifting back to the left. So for example, calculate the fluoride ion concentration and pH of a solution that is 0.2 molar in HF hydrofluoric acid and 0.1 molar in HCl, so it's already got some acid in there. The Ka for HF is 6.8 times 10 to the minus 4. So we take a look at our standard acid dissociation expression. You've got your concentration of acid, your H plus, your F minus, and then the initial concentration of the acid, and we set that equal to our Ka value. So just like we always done, we would ice this, but now instead of the initial concentration of H3O plus being 0, you actually have some already in there. We have some 0.1. And here's our initial concentration of our hydrofluoric acid, and we have none of this to start with. And just do this like we normally would. We have some change in X. Everything's a 1-to-1 ratio. And so at equilibrium, we make a lot of the same assumptions that we would have done before. Because this is a weak acid with a very small Ka, we can assume that this X is negligible compared to 0.20, so it remains 0.20. And again, if this is negligible there, it's negligible here, so this remains basically the same. And now we can just solve for X. So we plug this into our expression and then solve for X, and we get 1.4 times 10 to the minus 3. Now if we want to use this to get our pH, well, X is the concentration of F minus, the concentration of H3O plus is 0.1 plus that, so it's a very small amount, and hey look, with sig figs it comes out to be the exact same thing, just like we said it would be, so our assumption is correct, which is good. So it's 0.1 molar, so the pH then would be the negative log of 0.1, so a pH of 1, so a very acidic solution, which makes sense because it's got some strong acid in there. So a lot of this unit will focus on buffers. So buffers are solutions of a weak conjugate acid-base pair. And they're useful because they are resistant to changes in pH. They can even withstand the additions of a strong acid or a strong base. So as you can imagine, these are pretty common in nature. Like lakes and rivers have these to resist changes in pH from like acid rain, things like that. But your body obviously has lots of buffers to keep your blood at the correct pH and all your body fluids at the same pH. So pretty important. So if you had a buffer solution, so you got a weak acid, HF is a weak acid, and you have its conjugate base is F minus. So if you made a solution that was equal of those two equal concentrations, this is your buffer solution. It's got some concentration of hydrofluoric acid and an equal concentration of F minus ions. If we were to add a little bit of hydroxide to this, it's going to react with the HF to make F minus in water. So if we added a little bit of hydroxide, it's going to react with this to make water and then produce a little bit more of this. So this is going to cause the pH, this is basic, this is going to cause pH to go up, but this is going to cause the pH to go down, and they're going to kind of counteract each other, so the pH will stay roughly the same. Similarly, if we were to add an acid, that's going to react with the F minus to form hydrofluoric acid and water. So the F minus goes down, which means the pH is going up, but you're creating more of this HF, so the pH is going down. So they counteract each other. So there's one of the best calculations, one of the easiest thing to do is this very useful equation called the Henderson-Hasselbalch equation. And so just to show you how we get this Henderson-Hasselbalch equation, where it comes from. So you have our old friend here, the standard acid reaction, and a standard, our generalized acid dissociation expression. If we were to rearrange this a little bit, we can set our Ka equal to our concentration of H3O plus and our A minus over our HA, and we can take the negative log of everything to make this look a little bit more familiar to us. And so you end up getting negative log of these guys, negative log over here, and so this becomes your pKa. This then becomes your pH, and this is going to stay the same. So pKa equals pH minus the log of your concentration of base over your concentration of acid. And then again, rearranging just a little bit, because you're often looking for pH, so this makes a little bit more sense. pH of a buffer is going to equal the pKa plus the log of the concentration of base or the concentration of acid. So that's the Henderson-Hasselbalch equation. And this is actually also on your formula sheet for the AP exam. You can also use an alternate form of this if you had bases. So you just kind of replace this with base values. You have POH and PKB and the log of acid over base. So notice that's flip-flopped. With the acids, it was base over acid. But if you're working with bases, it's reversed. So you can kind of do either one. More often than not, you'll see the typical pH equals pKa expression. So how could we use this? So what would the pH be of a buffer that is 0.12 molar lactic acid and 0.1 molar of sodium lactate? So again, that lactate is going to be the conjugate base of the lactic acid. And the Ka for the lactic acid is 1.4 times 10 to the minus 4. So simply, we just plug this into our Henderson-Hasselbalch equation. So we're looking for pH, and we were given all the rest of these values. That makes that fairly simple. pH is negative log of your pKa, and then they gave you the concentrations of the base and the concentration of acids, and so we can calculate the pH 3.77. So if you needed to make a buffer, you could use this to help you figure out what concentration you might want. Another example, this one a little bit more complex. How many moles of ammonium chloride must be added to 2 liters of 0.1 molar ammonia to form a buffer whose pH is 9? Assume the addition of the ammonium chloride doesn't really change the volume of the solution, and the Kb for ammonia, because ammonia is a base, so it's Kb, is 1.8 times 10 to the minus 5. So there's actually 2 different ways you could solve this. The first one is you could use the Kb expression to figure this out. So here's your equation, your reaction. You've got ammonium plus the water is creating ammonium and hydroxide. And we have our Kb expression, so that would be a concentration of NH4, concentration NH over NH3. We're leaving out the H2O because that's a liquid. And we need to get the moles of NH4Cl, so we need to get concentration of NH4 so we can get that. So we have NH3 because we're basically going to assume it's not going to change. So to do this, we got to figure out what our concentration of OH is first. How can we do that? Well, we have the pH value. We would tell us that we're making a pH of 9, and so since we know that POH equals 14 minus the pH, POH then would be 5, and so if the POH is 5, the concentration of OH minus is 1 times 10 to the minus 5, so it's 1 times 10 to the negative pH. So now we have concentration of OH. And so we can just plug this in and solve for a concentration of NH4, which equals our Kb value times concentration of NH3 over the concentration of OH minus. And those values right here, and you get 0.18 molar concentration of NH4. And we know we had 2 liters of the solution that we're trying to get, so we need 0.36 moles of NH4Cl to get that. So like I said, there's a different way you could do this. You could also use Henderson-Hasselbalch. In this case, we're working with a base, so we can use that alternate Henderson-Hasselbalch. So first, to do that, we would have to get our pKb value, which is really easy to do because it's just the negative log over Kb, so 4.74, and plug that in. So we have our POH equals pKb plus log of acid over base. We already found our POH before, but if you're obviously doing this way, you would do the same thing. So our POH is 5, we got our pKb. We have log of NH4 plus is what we're trying to find. We were given the concentration of our base of 0.1. And so moving this over here is 0.26 equals log of NH4 plus over 0.1. Take the antilog of both sides to isolate the log part, and then you get 1.82 times 10.1 is 0.18. Hey, it's the same answer. Isn't that great? 0.182 times 2 liters and 0.36 moles. So two different ways of solving that. Some more information about buffers. Some things you might talk about is the pH range, and that's the range of values that the buffer really kind of works effectively. So depending on what pH you're trying to buffer at, there's different buffers that you can make. A good rule of thumb is you choose an acid with a pKa close to the desired pH. So if you wanted pH of 5, you're going to find your acid that's going to be a weak acid that has a pKa of 5, and then you figure out its conjugate base and mix it up with that. The buffer capacity is the amount of acid or base that it can neutralize before it really begins to, let's say, busted wide open, basically. There's to change dramatically. And so intuitively, if you increase the concentration of the buffer, then the buffer capacity increases. If you were to decrease that, it would decrease, right? Because you have less moles of our weak acids and weak bases in there to absorb the strong or weak acid or whatever it is that's being added to it. So a little bit about titrations. We've already seen some of this stuff actually in our last unit when we've done titrations before. But you guys know what titration is. It's when you're taking a known concentration of something. Usually it's a base being added to an acid, but it can be either way. And it's slowly added, and you can measure the pH, or you can look for the endpoint with an indicator or something to figure out when you get to that or near that equivalence point. So like I said, there's a couple different things. You could do a pH meter, or indicators can determine when you've got to that equivalence point. And so technically speaking, the equivalence point is when you have a stoichiometrically equal amount of acids and bases. Technically, if you're using an indicator, you're getting the endpoint, and the endpoint is when the indicator changes. And if you've chosen your indicator appropriately, that should be near the equivalence point, but not necessarily exactly. So for example, if you're looking at this graph here, this is the equivalence point right here when those are exactly equal, but depending on your indicator, your change is going to happen not quite at that spot. Now you notice the curve is very, very steep right here, so they're reasonably close. So depending on what kind of accuracy you're looking for and or what equipment you have available to you, you would choose to do an indicator and get the endpoint, or use a pH meter and get the exact equivalence point. So being able to recognize the titration curves of a strong acid or base or a weak acid or base is something you'll probably be asked to do. And it's actually pretty easy to tell. So if you're looking at a strong acid and a strong base, so like this is like what we did when we did our titrations way back at the beginning of the year. From the start of the titration, well, obviously if you've got an acid, you're starting very, very low, right? And this part here, it goes up, but pretty slowly until you basically start to get to that equivalence point. Then it's going to shoot up. Your pH is going to increase dramatically. So just before and after, it's going up very, very quickly. And then at the equivalence point, your moles of acid equals your moles of base. And so at that exact point, you just have water and then the salt from the cation of the acid or base. And then as you add more base, it's basically the other, same as the other side of the equivalence point. The pH is going to level off again and slowly increase. So that's fairly standard. And then your equivalence point is just pretty much what you've always been told. Equivalence point is 7. Acid plus a base gives you water, and it's salt. So hydrochloric acid plus sodium hydroxide at that equivalence point, the pH is 7, and you've got salt water. When you're looking at a weak acid or a weak base, things are a little bit different. More often than not, you probably see a weak acid. But so if we're looking at a weak acid with a strong base, so now if you recall, the conjugate base of a weak acid actually does affect the pH, right? So the conjugate base of a strong acid does not. So the Cl minus doesn't do jack squat to pH, but the conjugate base of a weak acid will. So at the equivalence point, you've got that basic ion hanging out in there. So your equivalence point is actually going to be greater than 7. So now this is going to be a little bit different from the definition you've probably always thought of when you're thinking of these. And we generally, for these guys, use the phenolphthalein as an indicator for these reactions. And so here are some differences you would see is the pH still starts pretty low, but quickly rises, right? So this is not nearly as flat as it was with your strong acid. You still have this quick increase here, but again, your equivalence point now, we're looking at pH of like 8.5 or something like that, and then it's kind of the same thing on the other side. So things to note, though, is just the fact that this shape of this curve, right, this is going to go up less gradually, a little bit steeper, and then definitely you would, if you were asked to like sketch a curve, you would, very important that your equivalence point, so it's like the halfway point of this steep, where the curve is the steepest, you would want to make sure that is in the basic range. So for weak acids, like I said, the equivalent, the starting point is a little bit higher, and that equivalence point changes. If you're doing a weak base with a strong acid, pretty much the same thing, except just flipped upside down. You're still going to start basic, and it's going to decrease pretty quickly. And here you are at your equivalence point, and now we're dealing with a weak base, so its conjugate acid does affect the pH. So now you've got some acidic ions swimming around in here. So you're at your equivalence point, the pH is now acidic. So phenolphthalein wouldn't be a good option here because this is the range over which it changes color. So for these guys, you would use methyl red. And they do like to ask you about that quite a bit. So that's a good thing to know. If you're dealing with a polyprotic acid, remember these guys are the ones that can donate multiple hydrogen ions. You would, if you were to titrate this all the way until you used up all of it, you would see multiple inflection points, so multiple equivalence points where you'd be able to tell when at this point you've kind of used up all your H3PO3, and then here's when you've used up all your H2PO3. So an example of these problems, something you might be asked to do. So calculate the pH of a solution when 51.0 mils of 0.1 molar NaOH, so strong base, has been added to 50 mils of 0.1 molar HCl. So this is a strong acid, strong base. So how do we do this? We've got to get the moles of our hydrogen and moles of our OH ions. And then we can figure everything out. So we know that we used 0.05 liters, 50 mils of HCl, and we knew its concentration, so that we know that we used, or we had 5 times 10 to the minus 3 moles of H plus, and then similar math, you would have 5.1 times 10 to the minus 3 moles of OH. And so now we can just ice that up. So initially, this is how much hydrogen we had. This is going to change, obviously, to you're changing this much because you had nothing. Now you added this much, and so you have a little bit left over. So 0.1 times 10 to the minus 3. So because 5 of this was consumed to neutralize the 5 times 10 to the minus 3 moles of H plus, so that leaves a little bit of that stuff left over. And so our new volume is 51 plus 50. So we got to add those volumes together, 101 mils. So now we have, we can figure out our concentration of our OH because we know the moles that are left over, and we know the milliliters of solution. So now we have our concentration, and once we have our concentration of that, we can get our POH is 3. And then pH is easy to get from there, pH of 11. Another example, this one more complicated. Calculate the pH at equivalence in the titration of 50 mils of 0.1 molar acetic acid with 0.1 molar sodium hydroxide. So we have a weak acid with a strong base, so the pH at the equivalence point is going to be greater than 7. So now we're going to be working with Kb, so we're maybe a little bit less familiar with. And we got to figure out our moles of acetic acid. So we had 0.1 molar acetic acid, we have 0.05 liters of that, 50 mils of that, so we have 5 times 10 to the minus 3 moles of acetic acid. And so the concentration of acetate at the equivalence point is going to equal the initial concentration of our acetic acid. Right? So if you think about that, you start off with this much, and at that equivalence point, we've turned all of this into this. So at the equivalence point, those guys are equal. So our concentration of our acetate ion equals that many mils, or that many moles, because the moles are equal, over our new volume. And remember, they're additive. So if you use 50 mils of this, since these are the same concentrations, you're going to use 50 mils of that as well. So now we have 100 mils. So, and then we have 0.05 molar concentration of our acetate ion. So we need that because, again, it's a weak base, and so we're using this. This is going to be our chemical reaction. That weak base is going to react with some water to actually turn back into acetic acid and some hydroxide ion. And so plug that into our Kb expression. There's that Kb expression again. We've got our acetic acid, our OH minus, and our acetate ion. And plug in what we know. Well, first we get our Kb. We add our Ka, so we can get our Kb from there. It's 5.6 times 10 to the minus 10. Now we can plug in what we know and what we don't know. So here's our Kb. We don't know these concentrations. We do know our concentration of our acetate ion, and we know it's going to change by some amount. I just iced this sort of in my head, but same idea. This is going to change by some amount. Solve for x, and x is 5.3 times 10 to the minus 6, which is also equal to this x, which is this, your concentration of your OH. So once you have concentration of OH, it's very easy to get POH. So it's 5.28, and from there, 14 minus 5.28 is your pH 8.72. It's a little bit more complicated.